To represent a vector, we will very often use an arrow. An arrow has a particular length. We could draw a short arrow. We could draw a long arrow. So a short arrow for a small vector, a longer arrow for a larger vector. And an arrow typically has a particular direction. We can draw our arrow pointing in some particular direction. We could say it points that way, it points that way, it points that way, any way we want. Now, I'll typically be drawing arrows in the board, but we'll also talk about three-dimensional arrows. We could have an arrow that points out this way, or down this way, or into the board that way. So we can describe different directions for our arrows. Or the arrow can have different directions. How do we describe the direction of our vector? Well, to do that, we will typically use a coordinate system, an x and y coordinate system. We'll often put our coordinate system at the tail of the arrow. So an arrow has a tip or a head, or and a tail. And I will often refer to the head of the arrow and the tail of the arrow. And when we add vectors or subtract vectors or things like that, do we want them tip to tail, head to tail? Do we want them head to head, tail to tail? What do we want to do? So we'll talk about that more later on. But typically when describing the direction, put the origin at the tail of the vector. Now, this is something that we will refer to often. Think about a vector like your arm. If my arm is like a vector, where does this vector start? It starts at me. So my arm points from me and then away. So starts at me, in other words, the tail of the vector is at me, and then the tip of the vector, the head of the vector, points away. If I were going to say, I'm going to go out that door over there, the door over there, I would point like that. I wouldn't say, oh, I'm going to go over the door over there and point it like this, pointing it at me. No, the vector starts at you, at yourself, and then points away from yourself. So always try to think of vectors as starting at the object, whatever the object is, and pointing from the object. In 1111, I tried to emphasize this, that when drawing forces acting on objects, the force started from the object and pointed away from the object, rather than pointing toward the object. It was just a way of being consistent and thinking about how the vectors are acting from the original direction of the object and then pointing away from the object. Okay, so how do we then describe the direction of our vector? Well, in this case, we might describe what the angle is between our vector and one of our coordinate axes. For example, we might say that this vector is at some angle theta. This Greek letter theta is a very common letter that I will use to describe angles. We might say that this angle between the x-axis and our vector is something like 25 degrees. Okay? So we could describe this vector v. Let me just make a mention here. When writing a vector, typically in textbooks will often write a vector in some kind of bold. And then when they want to talk about a scalar is a quantity that does not have direction. For example, the length or the magnitude of a vector is a scalar because the magnitude doesn't have a direction. The vector has direction, but the magnitude of the vector does not have direction. So if you want to talk about the magnitude of the vector, the textbook then will often write it as, and it's hard for me to do it, but in italics. So we've got bold for vectors and italics for scalars. Now typically when I'm writing on the board, when I want to indicate a vector, so these are vectors, and these are scalars, and this is often the way they do it in a textbook. And how I'll do it on the board is when I want to emphasize a vector, I will put a little arrow, a little vector sign on top, above it. And if I want to talk about a scalar, I will just write it without a vector sign. So the presence of that vector sign indicates that we're talking about a vector. Now, just let me emphasize that on iCollege, for quizzes and things like that, because of different computer formats, sometimes the vector signs don't always work, and so I will typically come back to this and write vectors in bold. So just if you're taking a quiz or an exam, kind of keep that in mind. All right, so there we go. So this vector v, it's a vector because we know it's got a vector sign there. So a vector v, we might say, has a magnitude of 15 meters per second. Maybe this is a velocity vector. And the direction would then be, we would say in this case, above the x-axis, 25 degrees above the x-axis. So to describe the direction of a vector, we need to give some kind of angle, typically, and then how that angle is measured relative to our coordinate system. We might say in this case that the vector v is 25 degrees above the x-axis. This is assuming this is the x direction, this is the y direction. We might also say, well, if this angle is 25 degrees, this would be 90 minus 25 degrees. What's that? 65 degrees. We might say that that vector is 65 degrees to the right of the y-axis. 25 degrees above the x-axis, 65 degrees to the right of the y-axis. Typically, vectors have two different ways that you can describe the direction if it is in, say, one of these quadrants, like the first quadrant, second, third, or fourth quadrant. You can say, what's the angle from the x-axis? What's the angle from the y-axis, up or to the right? Or, well, if it's over here, you could say this vector. Actually, let me make a general drawing, and then we can talk about how to describe the different vectors. Give me 1 second. Okay, thanks for waiting. So here we go. Here's our coordinate system. Here's our x-axis, and in general, we'll assume our x-axis is positive to the right, negative to the left. Our y-axis, positive up, negative down. So I'll refer to this as our x-axis. This is our y-axis. This is our negative x-axis, negative x direction. This is our negative y-axis, or negative y direction. So a vector in this direction, we might say, is 15 degrees above the x-axis, or 75 degrees to the right of the y-axis. This vector, we might say, is 30 degrees to the left of the y-axis, or 60 degrees above the negative x-axis. This vector, we might say, is 25 degrees below the negative x-axis, or 65 degrees to the left of the negative y-axis. While this vector might be 20 degrees below the x-axis, or 70 degrees to the right of the negative y-axis. So we can describe any of those vectors in those two different ways, using the angle from the x-axis or the negative x-axis, or the angle from the y-axis or the negative y-axis. Okay? Now, a very, very important result about vectors is that if the magnitude of the vector and the direction of the vector are the same between two vectors, those two vectors are the same vector. So we might have a vector like that and a vector like that. Now, if those vectors, I'll make two little vectors here, if those vectors have the same length and the same direction, in other words, if they're parallel, they are the same vector. So two vectors that are parallel with the same length, it doesn't matter where they are, as long as they have the same length and are parallel, they are the same vector. So that means if we have some vector up here and our coordinate system is down here, we describe that vector just like we were to move it down to our coordinate system. So This vector, even if it's up here, we would say that is above the x-axis or to the right of the y-axis. A vector that looks like this, even if it's way up there, even if it's like existing somehow up in the first quadrant, if that's the direction, we would say that vector is below the negative x-axis, below the negative x-axis, or to the left of the negative y-axis. You can either bring it down here to our axes, or just imagine bringing our axes up here. Either one, however you want to describe it. So the important thing is not where is the vector, the fact that it's up here, but what's the direction of the vector. The direction of this vector is the same as the direction of this vector, which is the same as the direction of this vector, which is the same as the direction of the vector if we were to put it right down with the x and y axes. Okay? Now, if you're in my class, there are actually some extra notes on the iCollege website. They're called Notes on Vector Directions, that you can take a look and look through those if you find that a little confusing. So, take a look at that if you want. All right, great. Now, sorry, one more thing. A vector that's actually on the axis, on one of the axes, typically we only describe that in one way. So if we have a vector right on the x-axis, we would say that that vector is on the x-axis, or on the negative x-axis, or on the y-axis, on the negative y-axis, or in the x direction, in the negative x direction, or something like that. Okay, now, another way of describing a vector, rather than describing the direction of a vector, rather than telling the orientation relative to the x, y, negative y axes, is to break it down into components, to break a vector down into its component parts. And there's always two parts, well, two parts if it's a two-dimensional vector, three parts if it's a three-dimensional vector. We will typically be focusing on two dimensions, but it extends to 3 dimensions very, very easily. So a vector in the xy plane, we will break down into two components. Now let's take a look at that. So let's imagine we've got some vector, maybe it's a velocity vector, with a magnitude of 15.0 meters per second, and it is in a direction so that it is 10 degrees above the x-axis. Now, rather than giving the magnitude and direction as a way of describing the vector, as I said, another thing we can do is break it down into components. The components tell us basically how much is the vector v pointing in the x direction, and how much is it pointing in the y direction. Now, to do that, we break this down into a triangle, and the length of the vector that points in the x direction, that's this part, and the length of the vector that points in the y direction, that is this part. This part we call v sub x, the x component of v. This part we call v sub y, the y component of v. Now, typically we'll draw these triangles and we'll write this as v sub x, v sub y, but to be very, strictly speaking, we're really talking about the absolute value of v sub x and the absolute value of v sub y for the lengths of the triangles. The lengths of a triangle are always positive numbers, but components, vector components, can be negative. For example, if the vector were to point in this direction, and I'll come back to this again in a second, it's pointing in the negative x direction. So the x component would be a negative number. I'll come back to that in a minute, but just for the time being, I won't always write these absolute value signs. Just keep in mind that components can be negative quantities. Okay. Well, what's the relationship between these things? 15 meters per second, that's basically the length of the vector, which is the hypotenuse of this right triangle. V sub x, that's the length of one side. V sub y, that's the length of the other side. 10 degrees, that's the angle in here. What's the relationship between these things? Well, there are some trigonometric identities that you really need to remember. If you don't remember these, you need to go over them and really commit them to memory, because we're going to be using them over and over and over again. Let's imagine we've got a right triangle here. A right triangle means a triangle with a right angle. And the sides are A and B, the hypotenuse is C, and let's imagine we know one angle, theta. Well, we know the relationship between the sides and the hypotenuse, the Pythagorean Theorem, a squared plus b squared is c squared. The cosine of an angle is always the adjacent side over the hypotenuse. The side adjacent to theta is A, so cos theta would be A over C, the adjacent over the hypotenuse. The sine of an angle is always the opposite side over the hypotenuse. The side that's opposite theta is B, so sine of theta is B over C. Well, multiplying by C, we have that A is C times cos theta. Multiplying by C, we have that B is C times sine theta. Now, these are the forms that I will typically use when comparing sides. I will jump right over the actual definition of sine and cosine, and I will use these. So remember, the basic idea is the adjacent side is the hypotenuse times the cos of the angle, so A is C cos theta, while the opposite side is C times the sine of the angle, the hypotenuse times the sine of the angle that's opposite B. So A, C cos theta, B, C sine theta. Then tangent of an angle is sine over cosine. Well, sine is B over C, cosine is A over C, so that's B over C over A over C. The C's cancel and we get B over A. So the tangent of the angle is opposite over adjacent, the opposite side over the adjacent side. Or theta, taking the inverse tan of both sides, is the inverse tan of B over A. Now on your calculator, the inverse tangent might be written as tan to the -1. It might be written as I tan for inverse tan, or INV tan, or A tan for arc tan. It could be written any of those ways. It just means the inverse tangent function. So that theta is the inverse tangent of B over A, the opposite over adjacent side. Now let's apply these to our situation over here. We've got a hypotenuse of 15 meters per second, and we've got sides of Vx and Vy. Vx is adjacent to the 10 degrees in this drawing. So drawing the angle between the vector and the x-axis, that is then adjacent to the x component. So in this case, we have the adjacent side, Vx, is equal to magnitude 15 meters per second times cos 10 degrees, while Vy is magnitude 15 meters per second, or hypotenuse, times sine of the angle 10 degrees. So we can multiply these out, and what we find is that V sub x is 14.8 meters per second. So make sure to keep those units with your components. So the components also have to have the units, the same units as the magnitude. While V sub y, which is 15 sine of 10 degrees, is 2.60 meters per second. And notice again, I've used 3 sig figs throughout. So what we have is that our x component, 14.8 meters per second, and our y component, 2.60 meters per second, those are the components of the vector. And they tell us how much does the vector point in the x direction, how much of the vector points in the y direction. Notice that Vx is much larger than Vy in this case, and that is because we have a relatively small angle. 10 degrees is a small angle and means it's going much more in the x direction than it is in the y direction. This is really not to scale. It really should look maybe more like that, a small angle. So Vx is much larger than Vy. Okay, there we go. So there are the components of this particular vector. What if that vector were pointing in different quadrants? Rather than the first quadrant, what if it was in the second, or the third, or the fourth quadrant? How would that affect the components? Well, let's take a look at that. Let's imagine rather than our vector being 10 degrees above the x-axis, it's 10 degrees above the negative x-axis. So rather than pointing to the right, it's pointing to the left. Well, in this case, we end up with a negative x component. V sub x would be negative 14.8 meters per second, while V sub y is 2.60 meters per second. Still positive. Why positive? Well, let's think about it like this. This vector points to the right, so the x component is positive. This vector points to the left, so its x component is negative. This vector points up in an upward direction, so its y component is positive. This vector also points up, so its y component also positive. What about this vector? Let's say same magnitude but 10 degrees below the negative x-axis. Well, then the x component would be negative and the y component would be negative. It's pointing to the left, so Vx is negative. It's pointing down, so Vy is negative. What about this vector, 10 degrees below the x-axis? Well, now it's pointing to the right, again, so Vx is positive, but it's still pointing down, so Vy is negative. So, the quadrant in which the vector is pointing determines whether Vx is positive or negative, Vy is positive or negative. First quadrant, positive x, positive y. Second quadrant, negative x, positive y. Third quadrant, negative x, negative y. Fourth quadrant, positive x, negative y. Great. What if the vector is exactly on an axis? What if the vector points directly on the x-axis? If it points along the positive x-axis, we would have a positive x component. What would the y component be? It would be 0, a 0 y component. What if it pointed in the positive y direction? We'd have a positive y component. What would the x component be? 0. If it pointed in the negative along the negative x-axis, what would the x component be? It would be negative. But what would the y component be? 0. If it pointed along the negative x-axis, what would, the negative y-axis, what would the y component be? It would be negative, while the x component would be 0. There we go. Very, very good. Another thing we're going to be dealing with is how to combine vectors. How do we add vectors together? Well, let's take a quick look at that.